Okay, in this video we want to look at vector algebra. Specifically, how can we represent a vector in terms of an algebraic equation? Now I've already seen a little bit how to do that with unit vectors. We're going to put that into practice and see some actual examples. So here we have a simple vector A, and we want to see how to write it as an equation, how to express it. And so what do we know about this vector A? So the first thing that we can see straight from this picture is that it is a vector that has been mapped onto an xy plane, and we can note that that vector has gone 1, 2, 3, 4 units over, and 1, 2, 3 units up. And so we can see the x component is going to have a value of 4 magnitude, and the magnitude of the y component, a sub y, is going to be 3 units. And if we apply the Pythagorean theorem to that, we can get that the magnitude of a itself would be 5 units. That, of course, makes sense. This represents a 3, 4, 5 triangle. But we can represent this vector in terms of either its components or its magnitude. But if we have just the magnitude, we also want to talk about the direction. And we know that the direction is going to be, so if this is the adjacent side to the angle theta, and this is the opposite side to the angle theta, we know that the tangent of theta is going to be the opposite over the adjacent, the y component over the x component. And to get theta by itself, we take the arctangent of that ratio, and that gives us 37 degrees approximately. And so we can express this vector in terms of either its magnitude and angle. So here we have the angle, here we have the magnitude, they go together, or we can express it in terms of the two components that we have. Now, in the previous slide, we started with the two components. We could see them directly from the graph, but sometimes you may, instead of knowing the components, you may know the magnitude and the angle, and you may want to find the components. And so here, obviously, we could read the components directly off the graph, but that's not always going to be easy or possible. So sometimes you may have to find out what the components are, and obviously we'll just use our trigonometry. So if we write down our components, we know that this distance here would be the a sub x value, a sub x, and this value here would be a sub y. And so we can look at their magnitudes and say that a sub y is the opposite side, a sub x is the adjacent side, the length of a would represent the hypotenuse. And so we know the relationship ax over a is cosine. That would be adjacent over the hypotenuse. And so we have the ax over a, adjacent over hypotenuse, gives us the cosine. And then we can solve for a sub x. Just multiply both sides by a, bring the a over to the right-hand side, and then plug in the numbers. We already know what the magnitude and the angle are, so we can just plug them in and look at what we get, 4, which is what we already knew it should be, but it's comforting to see that the math works out. For the y component, to solve for ay, we would do the same thing. We would say that ay over a would be the sine of theta. Solving for ay, we get that it's equal to 5 times the sine of 37 degrees, and that gives us 3. So either way, you can start out with the two components and find the magnitude and the angle, or you can start out with the magnitude and the angle and find the two components. So now we have what we need to write the vector A in terms of an equation. And you can see the vector A written in the generalized form. So a vector is equal to a sub x in the x hat direction plus a sub y in the y hat direction. A sub x and a sub y represent the x and y components of the vector A, respectively. And so these just represent numbers, and if we don't know what they are yet, we just leave them as variables. We call them ax and ay. If I had a vector b, it would have components bx and by, always in the x hat and y hat directions for the x and y components. And so I know what those numbers are from the last slides, so I can just plug them in, and I can say that a vector is 4 units in the x-hat direction plus 3 units in the y-hat direction. And of course, I could draw those in. I can draw that vector and that vector. And so I can say that I've got my AX here and my AY there. And so this vector A, tail to tip twice, is simply AX vector plus AY vector. But what's AX vector? It's 4 units in the x-hat direction. Where would the x-hat be? The x-hat would be 1 unit long, pointing in the x direction, would be my x-hat. So this is how we can look at this in terms of the directions defined by the x-hat and y-hat unit vectors. Now here's a different vector that we can look at. I've got A, but it's written in the second quadrant of the Cartesian plane. It still has the same magnitude, and it still makes the same angle with respect to the x-axis, but it's making that angle with respect to the negative x-axis. And so if I wanted to represent A in terms of components, my AX would be along this way, and that would be my AX, and then my AY would of course be vertical. That would be my AY. And so I could write out my AX and my AY, but look at the directions. AY is pointing in the y-hat direction, is pointing straight up. But AX is not pointing in the x-hat direction. The x-hat direction would be something like this. This would be x-hat. And so the AX is actually pointing in the negative x-hat direction. And we can see that here. So the vector A would be 4 units in the negative x-hat direction. That's 4 units in the negative x-hat direction, plus 3 units in the positive y-hat direction. I like to write it this way very often because it's very clear that the minus sign is showing you the direction. Remember, whenever you have a minus sign in a vector equation, that minus sign is always indicating the direction. It tells you that some vector somewhere is being flipped 180 degrees. But it's a little bit cumbersome to write it this way, and so most people will bring that minus sign out front. And so what you see here down below is the usual way that this vector would be written. It would be negative 4 in the x-hat direction plus positive 3 in the y-hat direction. And we can see that, so this is 4 units in the negative x-hat direction plus 3 units in the y-hat direction. That's what defines the vector A. Okay, here again we see the vector, but this time it's written in the third quadrant. Again, it has a 5-unit length, and it makes an angle of 37 degrees with respect to the negative x-axis, but in this case it's in the third quadrant. And so if I were to break this into its constituent components, I would get something like this, where I can draw a vector that has a x component and draw a vector that has a y component. And so this would be my AX vector, and this would be my AY vector. And notice that the AX vector, the tip of the arrow shows you the direction again. So this is pointing in the negative x direction. Here, my AY component is pointing down. It's pointing in the negative y-hat direction. So if I wanted to write my vector up here, it would be 4 units in the negative x-hat direction plus 3 units in the negative y-hat direction. And of course, I can write that in the usual way by pulling those minus signs out front. And again, here we have the fourth and final possibility for this vector of 5 units length and a 37-degree angle. And oops, there is a boo-boo here. This should be in the fourth quadrant, not the third. I apologize for that. So this is in the fourth quadrant, and as you can see from the vector, it's going to have a positive x component, and so we can see that the x component is positive 4 units. It's going to have a negative y component, and so that's going to be negative 3 units in the y direction, and that gives me that vector. And so we have seen that a vector can be represented algebraically regardless of what direction it's taken in. Usually the vector is represented with the reference angle to the x-axis, although I could choose another angle as long as I understand what I'm doing. But in terms of writing a vector as an equation, the two things that you need to pay attention to are how the magnitudes of the components change the lengths, and how whether you have a positive or a negative unit vector changes the direction.